So let me just remind you one thing. So what did we do? We defined absolute condition number, which measures absolute error. And the thing we found about it is if I know the solution map from input to output, we usually don't know. But in the examples we worked out, we knew this. I'm multiplying a vector with a matrix. The solution map is literally take x, send it to a times x. Right. Okay. Usually we don't know. We will do an example now that you don't know. Okay. But if you would know the f, the absolute condition number comes out as compute the Jacobian matrix, look at the greatest singular value of that matrix. Okay. And we also did the relative condition number that came out as, again, the same Jacobian and the operator norm, which is the greatest singular value, divided by how big is the output, divided by how big was the input. And we did this for multiplying a vector with a matrix. The absolute condition number came out as the operator norm of that matrix A. And the relative condition number came out as this operator norm of the matrix A multiplied with the operator norm of its inverse. And this is usually what's given as the condition number of a matrix. Okay. And this is only an upper bound. And the main reason for that is it allows this perturbation to be in any direction. And the other thing we discussed was this person, Bob Skeel, he looked at it a bit more carefully, and his reason was the thing allowing perturbations in any direction fails to explain structured systems. The easiest thing you could think of is like a diagonal system. Next level would be triangular system. And we did examples that condition number can be arbitrarily large. For a diagonal system, we still have one of them right there, right? 1 over epsilon. As epsilon gets small, it just blows up. But in practice, you solve these systems up to very good accuracy. Then he looked at it more carefully, and what Skeel realized is like if you constrain the change in the input to be in a certain direction, let's say some part of your matrix is 0, even if it is perturbed a little bit in your computation, 0 is 0, nothing's going to happen to that one. It's just going to be 0. Then you have to do it that way. And when he does it that way, the condition number he came up with was this one. Let me write this a little better and gives me also a chance to go through it. Basically, you take your matrix, you take absolute values of every single entry. There may be negative numbers, make them all positive. This is what this means. Absolute value, we usually take absolute value of a number, not a matrix, right? So this is another matrix. Do the same for the inverse. Now you have two matrices, multiply them, you'll get another matrix, okay? And then take the operator norm of that new matrix. That's his condition number. And we did this for this matrix, for example, the 1 epsilon 0, the diagonal, and we got, when we multiplied, literally the identity. And the operator norm will be 1 then. And the condition numbers is always at least 1, goes up to infinity. So this is the best you could hope for. So within Skeel's perspective, you understand why you solve these things with very high accuracy. And this is also a message of be very careful with your assumptions. Whenever you're doing any analysis of your algorithms that run over numerical data, be careful with your assumptions. That's the first message. There is a second important message, which I will not deliver today, but let me tell you so that you hopefully remember one day if you need it. If you are not sure about your assumptions, let's say Skeel was sure I'm dealing with structured matrices. Sometimes you don't really know what the algorithm is going to deal with, okay? Then another idea is try to run your analysis on some random input data. Because when you try to come up with guarantees for every single input data, usually you are very conservative in your estimates, and it starts killing your practicality. You can be conservative and you can be certified. You can say, if I use this much of precision, then for sure it's correct output. But you also want to be practical and actually cracking problems, right? So another idea is try to do your analysis if your matrices would be just random matrices or some sort of data assumption that models whatever problem you're dealing with. This is slowly taking off now. It's becoming a field called randomized numerical analysis. There is some growth, but it's not so quick yet, but it's slowly growing because it matches better between theory and practice basically than going to the worst case. Okay, right, pretty good. Now, let's do an example where we don't know the solution map, but still we will be able to figure out the condition numbers. How are we going to do that? Our example is this finding roots of a polynomial. So just the concrete example, we will do it for any general polynomial with degree 20, but this is a concrete example right here. This is called Wilkinson polynomial. I showed you a picture. I will show it again. This guy has roots 1 to up to 20. And if I would expand it out, it's going to be something like this, right? X to the 20, some number, X to the 19, something like that. And when you perturb these numbers, just after digit 10, this is what happens to its roots. Okay, this is the perturbation. And this is the cloud you get out of this roots. Okay, so this thing is more sensitive than you would expect. Now, then you would like to understand, how do I measure that sensitivity? So Ethan asked a very good question last lecture. His question was, if I only care about real roots, not the complex ones, can I do something better? You can do something slightly better. I did not check how much better it gets in Wilkinson's case. But in general, still it's not an easy problem. It still is sensitive if you only care about real roots also. Anyway, so I put the reference to our canvas. So we wrote a paper only doing real roots. If anybody's interested going in that direction, you can look up our papers, and I'm happy to answer any questions. We are not going to do that now. So now let me show you the technique. So our input is the coefficients of your polynomial. This is A. And our polynomial is this guy. PAX means A0, A1x, A19x, x to the 20. You give me the 20 numbers you need, and that represents the polynomial. And then every polynomial has degree many complex roots, fundamental theorem of algebra. The problem is going from the coefficients to the roots. Okay, that's our problem. And now we would like to understand how sensitive is this problem. Okay, so my solution map is F going from the coefficients to the roots, and the output is supposed to be 20 roots. This A is this vector A. Is it making sense so far? Let me just look at, say, the 10th root arbitrarily. Okay, that's a function. Let's just pick the 10th coordinate of this FA. Okay, you could pick any coordinate you like. You're going from that A, the coefficients, to the 10th root, and I would like to understand how sensitive it is to jiggling or to errors in the A. Okay, now I know theoretically this is what's going to happen. If I could compute the derivative of this map with respect to A, which is the Jacobian, and I take the greatest singular value, that's going to be the answer. But I have no idea what is that F. It would be super nice if you would know it, right? So you would just write down those functions, and you would solve stuff right very quickly. You don't even need any algorithm, but that's not the case. And there's even deeper math into this, right? We also know you cannot compute those functions using just radicals. This is Galois theory. Anyway, let me stop there. There's also some hardness, obstruction to even hoping for getting those Fs. But in practice, we can compute them up to some numerical accuracy pretty fast. Any package that deals with polynomials will have a command solve, and it will give you those roots. Okay, very good. Now, how do we go about this? I should look up to settings of the Zoom or whatnot. I used to ignore this, but it's becoming more annoying. Yeah, I forgot I was recorded. So now Zoom knows I'm very annoyed about that. Okay. Okay. So this is, now what do? We don't know this solution map, but there's one thing we know. Here is what we do. If you give me the coefficient matrix, coefficients A, okay, and if you give me a number X, maybe I should not, here X is not going to be a variable, it's just going to be literally a number, okay? If you want, I can change it. If it is confusing, some other letter would be fine, or are you guys okay? I can go change it. So what this is doing is, like, it's taking the coefficient Let's say it's going to be something like this. HA at 1. Let me write this down maybe concretely. So HA at, say, some number 2. It's going to go take this polynomial, PA, that corresponds to that coefficient, and evaluate it at point 2. Okay, that's what it is doing. It's literally an evaluation map. This we can do. If you give me 2, if you give me the coefficients, I can write down the polynomial, compute it, right? This we can do. Okay, very good. What is this any good for? So let's start taking derivatives with respect to these variables. Okay. Now, let me remind you what, so far the map is clear? Okay, so let me write it down. So what was PAX, just to have it here in our hands so that we can use it? It was A0, A1x, A19 x to the 19, x to the 20. Now let's take derivative of this guy with respect to A. What was A? A was my coefficients, right? So the output is a number. The input is 20 coordinates. So this is going to be like a gradient of a, it's going to be a vector, right? So what's the derivative with respect to A0? It's just right here, it's going to give you 1, right? What about A1? It's going to give you whatever that x is. X squared and x to the 19, right? This is this derivative. How about derivative with respect to x? Now everybody is going to get involved except this one, right? Let me write down. It's going to be A1, right? A1 times x with respect to x gives you A1. Then there's an A2 x squared. So what is the derivative of A2 x squared? 2A2, right? 2A2x, and goes until A19. It's going to give me 19 times A19 x to the 18. Then there's also x to the 20. It gives me 20 times x to the 19, right? Does it make sense? And I have a quicker way to write this. This is literally take the derivative of this polynomial, put it at x. This is what it is, right? So far, so good. Now, one thing I know, when I plug in a as the coefficient, and when I go to the 10th root, and then when I evaluate it, the output is going to be 0 because that's the definition of a root. Okay. Now let me take derivatives of this stuff on the left and right. On the left, you will get DAHA F10A plus DX I am trying to take derivative with respect to A, okay? Because everything here depends on A. On the right, certainly I'll get a 0. Give me a sec. On the left, I will get, I think, the following. I'm doing chain rule right now. DA F10A. Okay. And the Jacobian is literally this guy. I'm taking derivative of this solution map with respect to A, and I need to know how big is this. Okay. So this stuff here, this is depending on A. This is also depending on A. So everything depends on A. However, before I computed derivatives with respect to A and X. But I can do chain rule. Instead of X here, I got this, whatever that thing is. Okay, first I can take derivative with respect to X. Then I can go take derivative of this thing with respect to A, which is just chain rule, nothing else. Okay, all right. So you don't have to see everything through in algebra right now. It's not hard, but if you don't see every single detail, that's okay. You just need to see the punchline, which is just coming now. So what do I do? So what is this? Dx HA F10A. Well, F10A is a number. And we computed this guy right here, right? We have a general formula for it. So let me plug it in. So here I got this dAh at a f10a. And here I got derivative of this polynomial. And it was at x. My x is right here right now, f10a. Okay. Yeah, for once I scared myself when I said my x is right here right now. Okay, all right. So let's get back. All right, so far so good. Now what do I do? This is a number, whatever that is, and you can compute it. This is some number. If you would know it, you would be able to compute. You know, this is something right here, okay? Now I'll send this guy to the right. On the left, this will be what's remaining. On the right, the Jacobian I want multiplied with a number, whatever that number is, okay? But when you do all that algebra, what you get is this, your Jacobian, or you can also think about sending this to the right, dividing by that number. That sounded easy. Let me do that one. So I leave the Jacobian thing on the left. I send this stuff to the right and I divide it by the number. I don't know what this number is. Okay. Now I isolated the Jacobian I wanted to understand. So when you take absolute values, this is the stuff you wanted to understand on the left. Sorry, not absolute values, norms. And the norm of the stuff on the right. Okay. Now the expression on the right involves this h that I know what that is. It involves plugging in a number to the derivative of your polynomial. Okay. So let me try to make my handwriting a little better. F10. Yes. Okay. Give me a sec. Let me rewrite this, hoping it will look a little nicer. 1 over this number times okay. Now the thing here is, why did I do all that algebra? The thing is, I have no idea about this guy, but I only care about its magnitude. And on the right, I have something I can control. Okay. So this was a root of your polynomial. Now you're plugging in that number to derivative. Now here's the question. What's the worst thing that can happen here? If I get a 0 in the denominator, it will go to infinity, right? What does it mean to get a 0 here? That means the root of your polynomial is also a root of your derivative. Okay? So what does that mean? So we isolated the bad case now. What does it mean for the root of your polynomial to be also root of your derivative? I'm sure you all played with your quadratics, right? So this was our quadratic, right? X squared plus a, something like that. What's the derivative? 2x plus a, right? And the derivative is 0 at x equals minus a over 2, right? Okay. So if you look more carefully, the punchline is the following. The derivative and your polynomial vanishing at the same time means that root happens twice. For example, for your quadratic, it means the following. So let me show you a quadratic when that happens so that we make it concrete. Let's say this is your polynomial, x1 squared. This guy has root at 1 twice. Okay? Make sense? Maybe it doesn't make sense. What do you mean by having root at 1 twice? Okay. Okay, let's think about this guy versus, let's say 1.1 and versus x minus 1, x minus 3. These are all quadratics, right? Makes sense. Okay, good. Now, what are the derivatives for these people? The first one will have derivative 2 times x minus 1, right? And then you see 1 happens to be root of both the polynomial and the derivative, okay? The last one will have derivative what? I don't know. Let's see if anybody's quick at calculus. So I will get 2x minus 4, I believe. Okay. And the root of this guy is x equals 2, right? So the root of derivative is very different than your roots. Okay. So having the root for your polynomial and the derivative at the same time means double root. And why this is bad? This is very similar to this guy. How are you going to separate a double root versus two roots getting pretty close to each other? Okay. So the question is this. Suppose I just did not do 1.1, I did 1.000 then 1. I would put the 1 after your precision dice, basically. So the question is this. You got either this case. So let me draw them. So my case here will be this color, and my case here will be this color, okay? So this green guy is like a big 1 dot. And the other one is 2 of them getting pretty close. And you're asking your algorithm to differentiate between that and that. That's why it dies, okay? That's why the worst case happens when roots start colliding. Then you would see in the denominator here as 0, your condition number will blow to infinity. As you get closer to that case, you need more precision, okay? And this technique is very general. It's okay. I'm not going to claim it's the only technique, but the thing I saw the most when you have no idea what the solution map is, you do these derivatives, you move things around. You start with an easy map you can do, and that's usually that kind of map, like just an evaluation. What I was doing here is like, give me your A, these are your coefficients, give me your number X, then I can go compute this sum, okay? That'll be an easy map in the problem. Usually checking if that's the answer. I'm sure everybody in this class knows P versus NP. So we are hoping like checking if the answer is correct is easier than actually solving it. This idea is trying to turn it the other way around, okay? Start from checking the answer, take derivatives all over the place, and eventually isolate your Jacobian, which was looking monstrous. You didn't know what to do about it. Then you will have a formula for operator norm of the Jacobian, how big it is. Still, I admit the formula doesn't look terribly friendly either, but at least it's much easier than what the other thing was, okay? Then you start coming up with bounds and trying to understand where things die away, okay? At least it tells you it dies away when you got a 0 right here. From there, we were able to understand that means roots collision. If roots are separate without too much precision, you're able to isolate them. So at the end, what the solvers do, they don't usually find the root like extremely precisely. They would isolate that root in a very small interval. At the end, you need 2 intervals for 2 roots. If those intervals start colliding, then you have issues. Okay, make sense? That's the overall technique. And I would guess they didn't also tell you this stuff in those numerical analysis classes, right? Sure. Okay. So I redeemed myself so far. Yeah, I don't know why people don't teach this stuff, skill condition number or this technique, but I think they're very basic and fundamental. Yeah. There is, I hope even during that forward backward stuff, I hope to contribute a little bit. That's what I'm going to do right now. And that's all from me. I don't do numerical analysis for a living. I do research in numerical analysis a little bit, but people do numerical analysis for a living. They teach these classes and they don't talk about this stuff. I don't know why. So you have to ask those people. Okay. So I think these are very basic fundamental stuff. Okay. All right. Now about stability. So you need to first, before you talk about stability, you need to define what do you mean by stability, right? For example, if you're a dictator, What you mean by stability is don't elect anyone else, you will lose your stability. That's usually the trick. You first scare people, all of a sudden in places where dictators are strong, before every election, if there is an election, there will be some bombs, some explosions, people will be scared. Unfortunately, I have seen that so many times growing up. So that's not what we mean by stability, hopefully. So what we mean, we will try to define and make sense of it, okay? So stable, first definition numerical analysis came up with is something called backward stable. What does it mean? I think this diagram is useful to understand what it means. So let's say your input is here and your output is right here, okay? And then that's the ideal situation. Your input will have some error, and likely you will also add more error in your computations, and this is where you're going to end up with. Okay, so this is the error between the actual answer and what your algorithm spits out. Backward stable means the following: the thing your algorithm spits out actually corresponds to an input just a little bit away from what you actually wanted to compute with. What does it mean? It means the following: whatever your algorithm is spitting out, it corresponds to an actual input. This was the solution for this input, okay? That's why it's called backward stable. Your algorithm gave you an answer. That answer was just a little away from your input, but you can go backwards that way. That's the assumption, okay? And this type of stuff, if you can do it, it's called backward stable, okay? And the error between the input you wanted to compute with and the input your answer is actually corresponding to is your error. Okay. So the error is what the actual thing was versus what is the corresponding input to what your algorithm spit it out, okay? And that's going to be smaller than your machine epsilon. If you have it, it's called backward stable, okay? Very good. Now, examples. Let's say if you're doing inner product, you can sit down and prove that's actually backward stable. The usual formula you would write for inner product, x1 times y1, that's fine. How about doing this? You take two vectors. This time you're not doing inner product, you're computing x times y transpose, which is a matrix. Could that be backward stable, the algorithm you could come up with? So one observation, any matrix of this form is rank 1. Any objections for that? So yeah, you're having an error in terms of matrices in the output. Yeah. But we want a backward stable algorithm, or trying to understand if it is possible. So the question is this: I got this matrix. This is the actual correct one, right? And go back to diagram. There will be a perturbed one right here. The only thing I know about the perturbed one, it is this plus some error, right? It's a matrix A, where A minus your actual thing is less than some controlled error bound. But this tells you nothing about the rank of A. Okay, so you can be close to a rank 1 matrix like this, but you might be rank 2, rank 3. That means there will be no actual input corresponding to A that will get there. So let me draw the diagram, then hopefully it will make sense. Okay, let me go slow. So rank of A. So this is your actual. So this is rank 1 thing that you actually want to compute. Yes, now you perturb it, you go to an A. This is another matrix, n by n. And in matrix world, you have some error bounds. You know the norm of A minus the norm of the actual thing with a matrix norm, say Frobenius norm, is less than something, say epsilon. Okay. But to be backward stable, what you would like is this A to be corresponding to some perturbed input right here, right? But corresponding to perturbed input means A's got to be rank 1, right? Remember the diagram? But you have no idea about the rank of A. It could be rank 2, 3, whatever. You only know it's not too far in terms of numerical error from a rank 1 input. If it is not rank 1, there is nobody corresponding to that from backwards. So for this type of problem, you have no hope for a backward stable algorithm. Okay? And this is very common. If you are putting in some stuff in a space and pushing them up to another space, you have no hope for a backward stable algorithm usually, because of just following the definition. Okay, and this is almost always what happens in machine learning, right? I'm no machine learning expert. Let's ask Ethan. Don't you guys lift up stuff and add more, over parameterize? Yeah, right. So you know. Because this guy, to have a input corresponding to it, this guy has to have rank 1. It may be perturbed, but still rank 1. No. The definition. So what is this map coming up? So look at the diagram. So this should be corresponding to some other input. And what is our map? It takes the input, perturbed input, it will send it to this form, right? And this form is rank 1. But this A, probably not rank 1. So that means there's no such arrow coming back to A. I see you're very confused. So let me erase. Yes. So A is not likely not rank 1. It's likely actually full rank. Full rank stuff is dense. It's likely rank N. Okay. Ethan, question? Yeah. In math, it's a completely different discussion. There is no input you can choose that will spit out this A. That's basically what I'm saying. That's it. There is no more discussion needed. So every output coming off of your map is rank 1. That's a different discussion. Okay. Okay. So no hope for backward stable. Hopefully that is clear. Now, then you start relaxing your definition. The usual definition you would see in a lot of numerical analysis books is something called mixed forward backward stable. So let me tell you before I show you, I think even this is too restrictive. So I'll tell you one more, which you usually don't see in numerical analysis classes, which is more relevant to practice, I think. So what's mixed forward backward stable? It's a mouthful, as you can see. So what is it? So you got, let me go through this diagram if I manage. So X is your input and Fx is your actual output. Good. Now there will be some error. You will be right here. Okay. And now in the backward stable, you would like this output to actually correspond to some input jiggled a little bit, right? So let me go back to backward stable picture. The backward stable picture, what I wanted was like this output should be actually corresponding to some input, just a little bit jiggle. Okay. Now you are giving up from that. You're saying, okay, that was too much to ask. I don't even have it for like taking 2 vectors, making them a matrix. So let me relax. All right. So what do? You say, okay, I want still an input. The output coming off of it may not be what I computed, but it shouldn't be too far. Okay. Now you can imagine, for example, you can make this definition satisfied for the problem we were discussing. Okay. So this, you could find the rank 1 guy close to this A coming off from it. So you can make like mixed forward backward definition working for this. So you can come up with some jiggle here. It will go to something else right here. I don't know, let's call it L. And then between this, there wouldn't be so much difference. That would be mixed backward forward state. Okay. All right, very good. And the reason that I think you would mostly see this definition in numerical analysis classes is for linear algebraic stuff, for most of them, we have an algorithm that satisfies this definition. Okay. Then they were like, okay, this is our definition. We are able to come up with algorithms that satisfies this definition. They move on. This is numerical linear algebra people. But now we don't do numerical algorithms only for linear algebraic stuff. We do them for optimizing. God knows what you have to optimize in as a loss function. Okay. We use them all over the place. So this definition beyond the realm of linear algebra gets very restrictive. And even in linear algebra, we don't have algorithms satisfying this for all the things we want to do. Okay. Now, another definition that I think is relevant to practice is just forward stable. So you have, this is your actual input. This is your proxy for your input. This input, when I say input, it may be also say 10th step of the computation, right? We usually combine many algorithms, right? So when you see input, it may be just your data with some error. It may be your data got some error because of machine precision, or it may be you got data, you did some work, then this is going to be an input to the next algorithm. Okay, that's why we are only saying the error is some delta times how big your input was. And I did not quantify this with machine precision. For now, I'm just saying small enough. I'll tell a little bit more what that means. This is the assumption. Then you would ask from your algorithm, the output it spits out. F tilde means an approximation to the correct solution. F tilde is your algorithm. F is the actual solution map. X is the correct input. X tilde is what your machine is actually having to compute with, okay? The difference between your actual computation here versus the actual thing you wanted to do should be the error you got already in the input amplified by the condition number of the problem, okay? And the condition number, there is no way to get around it. It is the sensitivity of the problem, doesn't have anything to do with your algorithm or your machine precision. So this is some sort of reasonable definition to come up with. And just one second, Ethan. And this I would think is a bit more practically relevant because quite often you want to know how much error you're accumulating in your computation. That's usually what you care about, okay? And this gives you an edge to handle that, and it is a lot less restrictive than the other two definitions I showed. Okay, yes, question? I want to keep things simple. I don't want to make an analogy. Well, if you know content information, I don't know. There you go. You don't need to be sorry. All I'm trying to say is I'm trying to keep it as simple as possible. You know, that's not easy though. There's this, I think, quotation of Einstein: make things as simple as possible, but not simpler. Because if you try to make it simpler than it was supposed to be, then you start breaking the point. Sorry if I cut you. Okay, just that, you know, I don't know too much quantum information theory, so, you know, but I can understand this still. So okay. Anyway, so which part is not clear? Tell me. Okay, good. Exactly. That was the issue with this backwards data. And they usually get away by making forward and backward combined. But quite often, even that is hard to do in a lot of stuff we would like to do. We resort to just forward stable. And now the question is, let's say I got a couple of forward stable algorithms. can I just put them on top of each other and I'll still be forward stable? No, it's not that straightforward, unfortunately. Okay, so the issue is this. Yeah, so Chris is right at spot. Usually what do? You have a problem, right? Then you break it apart into smaller problems. Let's say I had a big problem. Then I said, okay, I'll solve this problem first, then the second problem, then the third problem, right? Then the first problem will have a sensitivity on its own. Second problem will have a sensitivity on its own. Third problem will have a sensitivity on its own. And then if you multiply all those sensitivities, it may or may not be similar to the initial problem sensitivity you started off with. If you're careful enough, and if your breaking down was good, if the sensitivity does not like amplify, then you'll be fine. You will still combine forward stable and end up with forward stable. Okay. So let me just draw a picture, and that will be end of my numerics discussion, or almost end of. So what I mean by that is this. Let's say you were going from here, right here. That was your problem F. Now that's usually what we do in practice, right? We divide it into different pieces. Let's say I solve it in 3 steps. I first do G, then I do H, then I do Q. This F will have a condition number on its own. It was going from X to Fx. Well, then these guys right here, they will have their condition numbers. G at X, then H is applied at Gx, then Q is applied at what? HGX. Yeah, that's right. Then you're going to multiply these 3 condition numbers. If it is similar to the condition number of the initial problem, you'll be fine. You will combine your forward stable algorithms for these 3 steps. You will end up getting a forward stable algorithm for the problem you want to solve it. Okay? But sometimes your algorithm, the way you break it down, maybe your algorithms for the pieces was good. Maybe they're important on their own, but when you combine them, your error just gets accumulated. And this happens very often if you try to put some arc cosine, arc tangent, even sometimes sine inside your computation. Those are very sensitive to combination. Okay. And there was a recent paper about this subject. They had a subsection called a very sinful function, and they were showing how sine can go wrong when you combine all over the place. Okay, so this is not some abstract nonsense mathematicians care about. Okay, this actually happens all the time, unfortunately. Yeah, exactly. That's and then even forward stable becomes very non-trivial. Maybe that's what I'm trying to get at. This was the most, so to speak, liberal definition that we come up with, right? That was backward, that was hard. Then combine backward with forward, a little better. Only forward was the easiest to satisfy. And exactly, as you all know, we will just use our library for here or there. That's how we go, right? That's what we always do. But then, even though I know this stuff, I rarely think about, what happens to the condition number amplification, but that stuff unfortunately happens. So when you would think about this, likely if things start breaking down in your computations, keep this in mind. That might be what's going on. Try to check your numerical precision in the steps. We usually think about this stuff when stuff don't work. Okay, unfortunately. Anyway, now the last thing I want to tell you is like a quick example. And exactly, the reason I thought about this is they come and ask me. They were trying to understand some issues in this computer vision 3D construction stuff. And this is just one of the small steps in that many step computation. So what they do, they take a norm with unit norm. Sorry, they take a vector with unit norm. X is somebody in Rn, it has unit norm. Then they have a matrix H, n by n. This matrix is invented by somebody last name Hartley, and this trick has 3,000 citations, I think now. Hartley's normalization trick. But nobody somehow analyzed the numerical aspects of the last step. And there are examples that is going to come up in the paper we write sometime this year, where the loss from the very last step washes away all the gains from all the clever tricks Hartley came up with back in the day. So you have to be careful. So what the very last step is very simple, and I don't blame anybody. You wouldn't expect any issues from here. Like X is there, you multiply it with the matrix. HX is another vector. Then you normalize it with the norm of HX to get a unit norm output, because their computation has to be unit norm. Okay, it's very projective type computation. Okay, and then if I had some error in X, how much error will be there in the Y? That's the question. Okay, and if you go through error analysis, the condition number, whatnot, you don't need to do it now. It comes out as follows. Operator norm of H, the bound comes like this. If I had some error in X, the error in Y, let's say this is my X tilde, and I compute Y tilde. Y tilde minus Y comes out to be less than the operator norm of H divided by this denominator HX times the error. That's how it comes out. Okay? And then, okay, fine. Usually, operator norm of H is fine. It's literally just a number like 3, 5, fine. This, you get some control on this, but this can kill you. If your X happens to be the type of X where HX is very small, then this goes to 0, it just goes away. And we, created a whole bunch of examples where this actually happens. Right? Okay. So that's all for numerical analysis. And if there are any questions you want to ask me now. And, otherwise I sorry? Yeah, because, this is important stuff, but not so much fun. So that's unfortunate part of numerical stuff. So it's important. It shows up all over the place. But it's a bit, hard to call it elegant. So you start getting bored of it after some point. Anyway, go for it. Yeah, condition number can be controlled if you have a bound for Lipschitz constant. So Lipschitz constant would be the following. If I have a map, I am doing condition number at a particular point X. What did we do? Jacobian operator now. Okay. And I'm doing Jacobian at a point X. Okay. And just to keep it simple, imagine you have just one function going from a whole bunch of input data just to a number. The output is literally a real number. Then what I call Jacobian is just like a gradient vector, right? So I'm literally talking about how big is the gradient at a given point, just point X. Lipschitz constant would be something more coarse. It will ask, what is the biggest possible gradient all over the place? Not at a particular point X, just in all your domain. That's what Lipschitz is, okay? So if you have a bound for Lipschitz, of course you have a bound for condition number. But usually Lipschitz is much more coarse than what we need to handle it. Right? That is a very good question. Okay, that's all numerics. I put some exercises on Canvas already.